So this is problem 7. This problem says crude oil has a viscosity of 0.07515 Pascal seconds. So let's make a note of that. Viscosity is equal to 0.07515 Pascal seconds. And density, so rho is equal to 858.5 kilograms per meter cubed. An oil rig is designed to pump 3 meters cubed of oil each minute. So volume over time is equal to 3.00 meters cubed per minute. What is the minimum diameter the pipes could be designed with in order to avoid turbulent flow? So we want to know what's the diameter of the pipes. So to completely avoid turbulent flow, we're going to want to be in that laminar flow region. So we're going to want our Reynolds number, which is equal to rho v d on the viscosity. Rho is the density, v is the velocity, d is the diameter of the pipe, and eta here is the viscosity. We need that less than 2,300 to ensure that we have laminar flow. So we're going to need to substitute in here. We've been given the density and we've been given the viscosity. We're going to need to work out the velocity here. So we can do that using our volume flow equation. We know that the volume over the time is equal to the cross-sectional area of the pipe times the velocity of the pipe. This gives us the volume of liquid flowing through the pipe per second. And so the cross-sectional area, this is a circle, so it's got an area which is equal to pi r squared, and then we'll keep the velocity, but we want everything in terms of the diameter, so the radius is half the diameter, so we can put this as pi d on 2 squared v, which is equal to pi d squared v, that's a v, on 4. So we've now got our volume over time, and we're told that this is 3.00 meters cubed per minute. So we should put this into seconds so that this velocity is then in meters per second as well. So in 1 minute there's 60 seconds. So we divide that by 60 like that. And so this tells us, rearranging it to get the velocity here as the subject, the velocity is equal to, this whole side is 0.05, so this is 0.0500 times the 4 divided by the pi d squared. So this gives us a velocity of 0.06366 over d squared. So we've now got the density and the viscosity and the velocity. So let's substitute this in. So we've got the density, 858.5, times the velocity, which is the 0.06366 over d squared, times d, over the viscosity, which is the 0.07515, has to be less than 2,300. Now this d squared will cancel with this d, so we'll end up with just 1d on the bottom. So we can work out the numbers on this side. This gives us 727.26 over d, and that has got to be less than 2,300. So that gives us d has got to be greater than 0.3162, and that's in meters. So we should give it to 3 significant figures, as this one here's to 3 significant figures. So this is equal to 31.6 centimeters for the diameter for our pipe. And then the question goes on, why is turbulent flow undesirable? Well, we want to minimize turbulent flow because it requires more energy to push the oil through the pipes when we have turbulent flow. So turbulent flow should be minimized to minimize the energy needed to push the oil through the pipes.